Okay, well, thank you for coming. So today's talk will be, well, in two parts. Brendan Everett is he was my student in kind of many of my STEPS courses that I offered, and he has done some of the actuarial and passed them, some of the actuarial exams. So he's going to give a talk about his experiences at an internship that he did in the past summer. And after he's finished with that, I'll give a talk on basically what I think would be a pretty okay introduction to probability theory. All right, so we'll get this started.
Good afternoon. My name is Brendan, as Dr. Ko said, and I'll be presenting a little bit about actuarial internships in general and my experience from this last summer. So I'm a senior here at Hope. I'm studying math and statistics with a little bit of business, economics, and data science. I've passed 2 exams so far. One was the P exam, which was following Dr. Ko's probability course, and the other was the FM exam, in which I used coaching actuaries. And I'll be sitting for the SRM exam in January. This last summer, I had an internship with Elevance Health in Indianapolis, Indiana. And I'll tell you a little bit about what the work was like there. So the structure of the internship program is for each intern to complete 3 to 5 projects in multiple lines of business, whether it's Medicaid, Medicare, or commercial. And this will be through different teams. So you'll have different mentors for each project you're working on, as well as an overall mentor that kind of guides you through the process of career choices and just kind of how you're viewing the actuarial field. And some important things that I did throughout the summer were spreadsheet automation, database querying, and regression modeling in R. And I'll talk about 2 of the 5 projects I did that kind of highlight those aspects. So the first one was a Medicaid global assumption upload template. So for a little background, a global assumption is one that we make for all markets and all products, markets being a whole state or a region of a state if it's larger, and then products being the type of insurance product that is being provided. So one example of this assumption would be a member growth assumption. So actuaries are very interested in how many members are using a certain product in a market. And the way that this was previously stored and uploaded was that there's a database that has all of the market and product membership for the company, and a user would have to go into an Excel spreadsheet, type in the market, the product name. They'd have to go find the current membership for it, and then if they want to assume, say, a 1% growth for that product for the next 6 months, they would have to calculate that themselves, and it's compounding growth, so that calculation gets a little tedious when you have to do this for over 200 products. So the goal of my product here was to have a template that they can use data validations in Excel and type the percent increase or decrease in this Medicaid product in, and then have that apply. It would pull from the database using an Excel macro and SQL queries to kind of input the current membership of that product, and then it would perform that growth assumption calculation you want on that membership, and then it would send it back to the database and upload it there. The second project that I had was a little less guided. So it was more of a look at one of the interventions that a health insurance company would be interested in doing. So one of the big focuses in the industry is cost of care and how they can reduce cost of care, both on their end and for their consumer. So one of the things that became especially prevalent with COVID was telehealth visits and in-home assessments. So we were able to collect data for the cost of care for all of the members in their database. But in order to compare if this intervention was actually going to be impactful on decreasing cost of care, we needed 2 groups that are somewhat similar. So for healthy individuals, like most of you in this room, it would be not a fair comparison of how much you spend on insurance versus someone who has a chronic illness. So we started by taking only the people who would be targeted for these interventions, and then we filtered based on if they accepted the intervention. So only about 10% of the targeted population would then accept it. So we wanted to see if those people would experience a decrease in cost of care over time. And we used regression to do this. And this was difficult because there are certain aspects and problems that come into play with using real data. People have somewhat of a selection bias if they're going to accept this intervention. So someone who may be spending more on health insurance already may be more likely to accept this kind of intervention than someone who is maybe spending a little less. So accounting for these variables was part of the challenge of the project. Some useful skills that I had throughout the internship and what I would kind of recommend you learning if you're going into an actuarial internship, or most internships, I guess, in the math world. But Excel formulas, and then alongside each of these skills is a correlating Hope class that you could take to kind of build those skills. Self-VBA, I don't think is taught at any courses at Hope, but it was very prominent in this internship at least. And then the other thing that was very prominent was AI prompting. They had their own AI tool that they could use within the company that didn't feed back to OpenAI, and being able to use previous coding knowledge as well as AI prompting, which was very encouraged in the workplace, was kind of able how I was able to learn VBA and be worthwhile. Some other aspects of this individual internship. There were 10 other actuarial interns, and they housed us on Butler's campus. So they're pictured here. There would be networking meetings that we were encouraged to partake in, and these would either be with people in the actuarial space or the finance space in general, just to get a feel of the company and the kind of work that they may be doing, because there's so many different teams to work on, and you're really only experiencing 3 to 5 of them over the 10-week period. They also really encouraged social events between the interns that they aimed to kind of reflect the work-life balance that they feel they have at their company, and if you are listed there. And finally, their mission statement is improving the health of humanity, so they wanted to impress this on us by a day of volunteering at a food bank, which is pictured in the middle. So a few words of advice, I guess, in finding internships. I would say look on job boards. LinkedIn has an alert feature that can kind of filter out by location or company even, and that can be helpful in your search. The Director Center also encourages Handshake. I'd say it's a lot easier to get an exam or an internship once you have one exam passed, but having two makes it a lot easier. And taking relevant coursework at Hope, rounding out your skills so that when you are interviewing with people, you're able to kind of read their job description and tailor what you've learned here to really focus on what they're looking for in their interns. Definitely helps you stand out. Yeah, that's really all I had. I'll hand it over to Dr. Coe now.
Thank you. Okay. So what I'm about to talk to you about is, as the talk said, is an introduction to what probability is actually all about. But I want to give a disclaimer. It's a combination of intuition and very technical. So don't worry, if you are thinking about doing the probability course in the spring, the probability course doesn't require that super technical stuff. The intuition part and the formulas, yes, but not the pure math thing that I'm going to get into, because this is a lecture for a math department. So, and I want to show the relevance of what some of you are doing in real analysis and how it actually comes in, but that's not part of Math 365 if that's making you alarmed. It's just to show you the link that real analysis is good for something. Okay, in other words. Okay, sorry. Okay, so let's start with something really basic. Okay, so imagine I'm doing free throws. Actually, you don't want to see me do one, but never mind. So let's consider attempting two free throws of me doing two. All right, just two. So the sample space is the collection of everything that could happen in this particular experiment. All right. So if I'm doing two free throws, what are things that can happen? So this is pretty basic. So you might, okay, I might succeed both times. So yes, I might fail the second time or fail the first time, or I might fail both times. Right? So easy, this is easy to digest at this point. The key thing I want to bring about here is this kind of sample space is not only countable, it's finite. Okay, so uh, and we'll get to that in a minute, but finite sample spaces where there's an actual number of elements is the easiest to visualize and to understand. It's also the least problematic, all right? Okay, so sample space collects all outcomes that you may possibly see when you conduct an experiment. And by the way, we use the term experiment in statistics for anything that you attempt and record. It's not an experiment in the biology or chemistry kind of context, right? Okay, so let me ask you a question. If I were equally likely to make the shot as not on every attempt, and if I assume that my attempts were independent, what would I assign as the probability of any one of those outcomes which I listed happening? Anyone want to try? If I don't learn anything from every time I throw the ball, and all my throws are independent, and I will equally likely as not to make the shot each time, what would I assign? What would be a sensible assignment of the probabilities to any of these outcomes? Anyone? Yes.
Like a 25%?
Very good. 1 in 4. Good. Now, so this is the intuition part of the thing that I'm talking about. See, so most of us, I wouldn't say all of us, most of us are born with an innate ability, I guess, to do probability when it has a kind of a symmetry. It doesn't come to everyone. I remember, I watched one episode of the Jimmy Kimmel show, and they like to go on the street and ask people questions and all that. There was one where they asked, if I had a fair six-sided die and I rolled it, what's the probability I get a 4 or something like that? So most people were able to say 1 in 6, but one person answered 1 in 7. So to me, that shows me that not everyone has this kind of innate ability, but most of us do. That kind of intuition helps us, but can sometimes be a hindrance when you're doing things which are less intuitive. And you notice the word I've used is like, what would you assign as the probability to any of these outcomes? Because probability is essentially an assignment. And do you know, actually, when you take a probability exam, you can actually argue that an answer that you give, which is wrong, if it is internally consistent with the rules of probability, is an acceptable assignment. Now, what I just said is tantamount to like sacrilege, but basically, a, a probability system is actually a set of rules of the game. And as long as you agree to the rules of the game and you are internally consistent within the rules of the game, your answers are correct. So why are there probability exams? Why is there a P exam? Why are there correct answers? Is because the assignments you give to a probability assume that you have an inherent built-in experience of what we call frequentist long-run behavior. It's very hard to explain to someone why you said 1 in 4. Do you realize it's actually very difficult to justify why we all know if there are 4 outcomes and they're equally likely, yeah, we would assign a probability of 1 in 4. It's because back in our mind, we know that if I did this a gazillion times, under the conditions that I said, that I would assign. This kind of thing would happen 1 time in 4. So today's talk is not actually about finding answers to probability questions, but I'm getting more into the rules of the game and why probability works. So we are going to work with assignments that come from a very intuitive standpoint, from a frequentist. We are all, as we live, we are exposed to frequentist arguments, and that's actually what builds into your head the ability to answer questions like this. So what I'm saying is this. An assignment could be an insane one where I just say the answer is 1 in 3. If I did that, all my answers would not tally with the frequentist understanding of probability. But if they are consistent with the framework, the rules of the game, then it will be internally consistent. Okay, so it's kind of like telling lots of lies. Okay, if you tell lies, as long as you keep track of your lies, then it's hard to disprove what you're saying. All right, so it's like if I start from a premise that's not true, but if I build up on that, and some people build their life relationships on things like that, right? They build everything on a lie and all that. Okay, so probability theory is like that. You can build everything on a lie, but if you're consistent, then it's okay. It's just that it will have no bearing on real life. All right, so let's ask you something else. If I were equally likely to make this, I would say it's 1/4. What about making it at least once? So the language of saying making it at least once means that, well, once or twice. And we kind of know that the way to answer this is, actually, let me ask you, if any of those outcomes is 1 in 4, and I'm making 2 free throws, what is the probability of me making at least 1 basket?
3, 4.
That's right. What did you do? You took the outcomes individually. Each one's 1 in 4. There are 3 that qualify, and you added them up. So that's why probability has a very, very intuitive starting point. Everyone kind of knows that's it. And do you know what the answer will be failing both times? Right? Isn't that 1 in 4 as well? Where does that come about? Well, in 2 ways. You can see that failing both times is the opposite event of making it at least once. So you can either do it as 1 minus 3/4, or notice that in the original list of outcomes, there was one outcome where I failed both times. So there are 2 options. Why am I doing this? Because I'm trying to show you that you inherently know more about probability than you think. There are 2 ways to do this problem. You either look explicitly at the event of me failing twice, or you look at all the cases that I am not failing twice and take those away from 1. So we kind of already know this. I mean, the probability that it rains tomorrow, let's say, is 25%. We kind of know that the probability it won't rain tomorrow is 75%. What are you doing? This thing is 1 minus the probability of the event that you don't want. That kind of thing. So let's just do up this a little bit. Let's say I were twice as likely to make the shot as not on each attempt. So a slight twist now. And my attempts are independent of each other, and I'm still doing 2 free throws. Can anyone tell me, what are you doing in your mind when you try to give me the probability of succeeding the first time and then failing? Anyone want to try? What is the probability of me succeeding once or first time, failing the next, if I am twice as likely as not to make the basket each time? Anyone have an answer for me? What do you think? Anyone want to try? Yes.
2 9.
Very good. What are you doing?
You take 2 events and they're independent, so you multiply.
That's right. The fact that I told you you're twice as likely to make the shot each time means the probability of you making the shot any time is 2/3. If you assume independence from try to try, and I want to pass and fail the second time, I'm doing 2/3 times 1/3, so you get 2 9s. Very good. Why am I doing this? You can see once again that, and you can answer a variety of other things. Getting a no first and then a yes is the same thing. The probability is, it's not the same event, but it's the same probability. And no is it's also the same argument. You have 1 in 9, and then yes in yes, you can also count this way. Now look at this. Okay, I'm going to show something else. If you added these up, you get one, two. All right. So the point I'm trying to make is whatever assignment you make to the probability, a few rules have to apply. First of all, you can add. It seems to be possible to add probabilities of outcomes if they fulfill something, and we'll get to that more carefully. Didn't you do that just now when I said I want to succeed at least one time? So you add up all the cases which qualify. So the addition rule seems to be there. The complementary rule seems to be there, where if I wanted to find the probability of this happening, if I already know these three, I don't have to do any work to get this one. I just do add up all these and subtract from one. See, these are all somehow they're very innate. Everyone seems to know that these things have to be true, right? But are the answers the same as what it was? It wasn't, because the setup, the assignment of the probability has changed, but the rules of the game are the same. Okay, so because here I'm saying I'm twice as likely as not to make the shot. Previously, I said I'm equally likely to make the shot or not. You get different answers, but the underlying rules are the same. All right. So if I wanted to answer the question, making it at least once, you add up those cases. So as I talked about, we have done a few things naturally. Kind of like all of us have a first language. No one actually needs to learn the first language. You learn it by immersion. Basically, you listen to your mom, your dad speak. So you don't learn the rules. So even no matter how complicated a language is, you kind of know. And these are something like that. Everyone seems to know, well, most people seem to know that you can add probabilities of outcomes to form the probability of a joint outcome, if you like, call it event, as long as those outcomes were disjoint. They have nothing to do with each other. They can't happen together. If I succeed the first time and fail the second time, I can't do that at the same time as failing the first time and succeeding the second time. So they're called disjoint events. If the events are disjoint, to find the probability of them all together, any of them happening, you can add up the probabilities. So that's one. The other thing we talked about is we all seem to have this idea that the total probability of anything happening has to sum to one. And if you know the event of one event happening, if I want to find the complement of the event, the opposite, I know that I can subtract it from one. These, you don't need me to tell you these things. We kind of know these things already. Okay. So let's move on to something slightly more complicated, and you see where I'm going with this. In the first example where I talk about just two free throws, the sample space was a very easy one. It had 4 outcomes inside, and it's finite. The next wrinkle, if you like, is when you still have a countable sample space, but it's now infinite. Now, what do I mean by potentially infinite free throws? So if I were to keep attempting free throws and only stop once I make my first one or I succeed for the first time, what would my sample space look like now? Anyone want to try? Just use the letters Y and N. What would the sample space look like now? So you understand the setup? I will keep throwing until I succeed, and once I succeed, I'll stop. Yes.
Like N, dot, 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 Y.
Yeah, that's one number. Good. So do you agree that the sample space has to kind of look like this? I might succeed in my first try. So that's a yes. Or fail first, then succeed. Or fail, then succeed. In fact, actually, it's kind of morbid, but this is kind of like the model for taking SOA exams. Right? If you pass, once you pass, you don't take them again. But you try until you pass.
Or you just give up.
Or you never pass. So it's like potentially infinite free throws. Okay. So the moral of the story, this is countable. What? Okay. First of all, can you argue rigorously why this is to you mad people here? Why is this countable? It's infinite, but why is it countable? Anyone know the formal way of how do you explain to someone rigorously that something is countable? What's the criterion that you need to check? We know inside we kind of know this is countable. Yeah, what makes it countable? What do you need to say? Does anyone know what? Yes.
You need to have a one-to-one mapping from the actual pointers to the events that are occurring.
Exactly right. And isn't there a very natural mapping? This is there's no n here. Here there's one n, there's two. That's all you need. So if you can find a mapping to the natural, or you can go either direction. If you can go from the natural numbers to this, that makes it comfortable. That's the rule. So this is infinite. It's potentially, I might never succeed, and it's countable because you can map the outcomes in S to the natural numbers n. Good. That's right. Okay, so this is the second kind of sample space. So the first one was finite. This one is also something that behaves quite easily and well. There are not many problems with this kind of sample space. Okay, so let's ask you a few things. Okay, once again, if I were twice as likely to make the shot as not on each attempt, and my attempts are independent, what would I calculate the probability of no, no, yes to be? Anyone? If you want, you can just tell me what would you do to get the answer. It's a product, right? What would you multiply together?
One third, and 2/3.
That's right. That's right. So the answer is you would assign 2 out of 27 if this is the setup that you agree on. 2 out of 27. Very good. So that's right. So if I indexed all my potential tries in this situation, every term in the sample space actually looks like this. You see? And the number of n's follows the index I. Okay. And do you agree that the probability that we will assign to any of these things happening has to be of this form you just said? 1/3, 1/3, 2/3. That was for the case where your I was 3. And therefore, do you find that okay, what is this sign? You will notice that I have conspicuously and purposely left out the infinity symbol. You will not see it in this entire talk. And there's a good reason. It is one of the most maligned and misunderstood things, and I don't want to put it there, right? This just means what is this set is I'm a member of any AI you can imagine. When I do this experiment where I infinitely or potentially infinitely throw a ball, don't I have to be in one of the AIs? And doesn't this probability have to, in the end, sum to? And the answer is no. See? The previous examples where the experiment was limited to just 2 throws, the sample space has a probability of the sum of the outcomes also summing to 1. This is also true. See? So these are things I'm trying to build up to a conclusion. So now this is the famous geometric series that you've probably seen. Again, I don't like the term sum to infinity, and I have left that out. But you should know how to do this, right? Anyone remember the general formula for geometric series? It's a fraction, right? If I know the first term is a and common ratio is r, what is the sum to infinity of a geometric series? Anyone? If anyone, it's a fraction, right? Yes.
Then like a times 1 minus r n plus 1 over.
Oh, okay. I like that. That's a very good try. That's actually, if I want to sum, it's a parentheses 1 minus r to the n over 1 minus r. That one is if I want to add a finite number of terms. Very good. If you take the limit of that, actually you get a over 1 minus r. That's something that you might have seen before. And that's actually how you get the answer to this to become 1. So the answer is 1. So the objective of this part is to show you that, once again, all the outcomes in the sample space, the probability that you assign to them, if you are going to be internally consistent, has to sum to 1. If this is not true, that means your assignment is faulty. Something is wrong here because you don't follow the requirement that we all want. All right, that the total number of outcomes inside any of them happening has to sum to 1. Okay, I would also point out, please note, every one of these outcomes is disjoint. You can't get NNY and NNY happening together. right? The fact that that happens means that the other things didn't happen, right? So it's disjoint. So again, this is a repeat of the slide. Whether the sample space was finite or whether it's countable but infinite, again, we obey all these things. We find that you can add probabilities of outcomes that you want as long as they are disjoint. The total sample space must be assigned a probability of 1. If it doesn't, it means that your assignment is faulty. And the complementary events can always be found. Probabilities of complementary events can always be found by doing 1 minus the probability of the event that you don't want, actually. All right? Okay, so these are, again, a repeat. Now comes the slightly more technical, but it is not hard to understand. The reason why this sigma algebra complication needs to come in is because there are issues if you try to assign probabilities to sample spaces that are not countable or uncountable, if you like. That's where problems and funny things start to happen. And so this is a necessary detail. What is a sigma algebra? First of all, it is an algebraic structure. I know in this school, Math 341 is a course name, but what is Math 341 all about? Well, it's about algebraic structure. You learn about different entities, if you like, that follow certain rules and have certain symmetries and properties and all that. That's why it's called an algebraic structure. Sigma algebra is one of them. You might see this called something else, all right? In sigma field, I believe is the same thing. I think so, but from a probabilistic standpoint, we always say algebra. So what is a sigma algebra? A sigma algebra can be thought of as a huge container, and it's a container of sets, smaller sets inside. What must be true of a sigma algebra? Well, it's a container that has to obey certain things. It must have the empty set. It's a container that has an empty container inside as well, if you like, right? The entire sample space is also part of the sigma algebra, all right? So it's kind of like a huge thing that gobbles things up. So it's a collection of empty set, the original sample space that gets thrown into the collection itself, and then a few very interesting properties. And you will notice some of these, if your minds are in tune with what we're talking about, you will notice that these are the things that we dealt with earlier. If you have a set that already is in the collection, the complement of that set must also be there. Kind of like some people, right? You never see one person without the other friend, right? Something like that. You always see them together. If this is here, the complement has to be there. If this is not followed, you do not have a sigma algebra. Then a few more complications. If all these are members, A1, A2, they're all sets in the collection, the infinite union of them must also be in the collection, not a finite one. So it doesn't mean that if I have an infinite number of sets, but only a finite number when I put them together, that's not enough. I want everything to be there as well when they're all together. And if all these sets are there, the intersection of them infinitely as well has to be in sigma algebra. Okay, so a lot of technical stuff, but we will slowly revisit this. Okay, so just think of the sigma algebra as a huge container, and there are sets inside it, and these sets have to obey these properties if you want to be called a sigma algebra. All right. So let's check whether these things qualify as sigma algebras in the first place. Think about this very small collection. This is like a bucket. This bucket is a pretty sad one. It only has the empty set and the sample space. But do you know that's a sigma algebra? It qualifies. Because you will find it fulfills every criterion that I talked about. Think about it. Was the empty set in that collection, that small one? Yes, I told you that's how it's defined. Is S there? Yes. Since there are only two sets inside, let's go one by one. What's the complement of the empty set? Isn't it S? Wasn't S inside? Yes. What's the complement of S? Everything? empty set. Wasn't empty set inside, yes. So it's kind of, this is a very trivial example, but it shows you that a sigma algebra need not be something very complicated. This does qualify, as does this. This massive collection also is a sigma algebra. Now take a good look at this. Notice how complicated it is. What's going on? I have my original two. You have to have these. If not, you don't qualify to be a sigma algebra. But what have I done? These are not just collections of outcomes, but they are subsets of the original sample space. As I told you, a sigma algebra is a bin or bucket that collects sets. These are all the possible subsets I can form of the outcomes. Why is it so complicated? This has a name. This kind of complicated structure is actually called the power set of the original set. So if your original set has only 4 items, yy, yn, ny, and nn, you can actually think of it in terms of a combinatorics kind of argument. How many ways can I pick nothing, one thing, 2 things, 3 things, and the entire thing? How many ways can I form different collections of things that come from it? This, if you can list them all down, that's called the power set. Like that. So this is actually the largest sigma algebra you can form for a finite sample space that you start off with. All right. So let me ask you, if I want to deal with probability problems, which sigma algebra is more useful? Do you think this one's an interesting one? This is not a very interesting one because you can't talk about very much. You talk about nothing or everything. If you want to talk about anything in between, you're going to need something a little bit more detailed. And that's why we consider other sigma algebras as well. So move on. This is not useful, as I said, because if I were to assign probabilities to the members here, what would I have to do? The probability of nothing happening or none of those things happening is 0. It's impossible. If I do 2 free throws, something has to happen. You cannot have none of those things happening. So I must assign 0 to this one. We know the rule. The entire sample space 1. You're kind of stuck. There's nothing else you can do. Your sigma algebra has too low resolution. You can't say anything more. You're not saying wrong things. You're just not saying interesting things. That's all. All right. On the other hand, F2 is a sigma algebra that contains every event you could possibly be interested in a 2 free throw situation. And you can't think of anything else that you could be interested in either. All right, because it's a finite sample space. So in probability problems with countable sample spaces, the default sigma algebra is the power set. No questions asked. That's the default. So as you move on, what is a probability measure? And here's why it was needed to define a sigma algebra. A probability measure is a mapping from that bucket, the sigma algebra. Sigma algebra contains sets. It assigns values to sets. And it assigns them in a way that is consistent with our understanding of probability. What are some of the things that you want? You want to assign a probability value somewhere between 0 and 1 for anything. That's rule number 1. You want the probability of the empty set to be 0. You want the probability of anything in the original sample space happening to be 1. And it is a desirable thing that if you have a countable collection of sets and they are disjoint, the probability of any of them happening is the sum of the probabilities of each of them happening. Do you realize this is formalizing things that you kind of know at the back of your mind and we already did previously? All right. These axioms are so famous and they were formalized simultaneously, actually. A lot of probability theory, interestingly, developed on parallel tracks. There's a Russian track and a non-Russian track because at that time the Soviet Union was close to the world. So they actually discovered things at the same, almost the same rate, sometimes a little bit faster. These are attributed to Kolmogorov, right? And they are axioms. You can't prove these things. These are things you want because they are desirous to us. They give us an inherent knowledge of probability that we are all comfortable with. These are the rules of the game. So you can't ask the question, why is PS 1? Because I say so. You can't prove these things. These are axioms. These are the rules of the game. Can you ask in Monopoly the first round you can't buy property? Don't play Monopoly. It's a very okay. But the point is, you can't question the rules of the game because that's the game, and you can't question these things because if you keep these rules, you will get an experience of probability that you're familiar with. That's kind of the reason why. So probabilities are only defined for elements of the sigma algebra. Outside the sigma algebra, you are not allowed to ask what is the probability of that event. You might be thinking, what? Why is this even a thing? If you have finite sample spaces or countable sample spaces, and if you use a sigma algebra that encompasses everything, you can ask any probability question that you like. It won't malfunction. Funny things happen when your sample space is not as easy. So let's talk about this. How do we prove this pretty simple result that the complementary events probability is 1 minus the probability of the actual event? I'm going to go through this quickly, step by step. Do we all agree that the entire sample space, A is any set, the union of A and A prime must constitute S? Yeah, you're either A or you're not. Okay. We also know that PA union A prime can be split up this way. Why? Because are A and A prime disjoint? Do they have anything in common? They don't. That's why it's called A prime. We are using Kolmogorov axiom 3 here to allow us to make the jump from this step to this step. Then we are using axiom number, I don't know what, 2, that says that PS is 1. That's actually how you get this. Do you realize that we often prove this in elementary probability textbooks by drawing pictures and coloring in Venn diagrams? Did you see that before? What kind of proof is that, right? It's drawing, okay? But it gives you intuition, but this is actually how you prove it. All right? You need the axioms first, the rules of the game, and you need this statement to start with, and to realize that these two are disjoint. All right? Okay, let's move on. What is the uniform probability distribution? It's very easy to visualize. Imagine a ruler marked 0 to 1. The uniform probability distribution assigns equal weight to any interval there. So the probability of you lying anywhere between 0 and 1 is 1. The probability of you lying between 0 and 1/4 is 1/4. The probability of you sitting somewhere between one quarter and 3/4 is half. So it gives equal weightage to everything like that. So you define the probability of being in these intervals always as B minus A. The probability of you turning up within A to B is B minus A. It's the length of that interval. And because single values like this have no length, we assign a probability of 0 to individual points on the ruler. Okay, so this explains why the union of these two, what am I doing? The probability that I land here or here is the sum of these two individually, because these two are disjoint. It cannot happen at the same time. All right. So if we move on, there is something called the Borel sigma algebra. Every sample space needs a sigma algebra. There is something called the Borel sigma algebra that is a suitable collection big enough to talk about subsets of 0, 1. There is no time left to talk about this. Just know that this is a massive collection that qualifies as a sigma algebra. It is beyond the scope of this talk. But it is important to talk about this because everything is based on what we know. You know how to count how long an interval is. And even though the Borel sigma algebra may be very complicated, it all boils down to intervals again. So let's talk about something that looks like a contradiction. We know that the interval 0 to 1 is the union of every single item of 0 to 1. Do we agree with that statement first of all? Isn't 0 to 1 the union of every number that exists in 0 to 1? It is. We also know that the probability of you lying somewhere in 0 to 1 is 1. That's the ball game, basically, for uniform distribution. However, isn't it true that if I single out every dot and count the probability, don't I get a big zero? Because every dot has no length. This looks like a contradiction. Didn't I just say the total space is this? Didn't I say the probability of the entire space is 1? Yet, if I sum up one by one like this, I get nothing. Can anyone point out the inconsistency? There is no contradiction. What have I done that's illegal in that sense? Yes.
Have you ever considered the other possibilities of the intervals? Have you ever considered the fact that there are other elements in this set that would actually hold weight, whereas all of these don't?
That's a good point. But am I wrong in saying this? Isn't this correct? Isn't the union of every, we call it singleton set, every set that sits as an individual number, isn't the combination of them going to be 0 to 1? And doesn't everyone have know it? So what is going on? The key thing is this. I have made an illegal move by saying that the probability of this is the sum of the probabilities of this. I cannot do that, and can anyone tell me why? Which axiom am I not following? If you go back to Kolmogorov, there was that word. You can only add up probabilities if the events that you're considering are a countable list. This is not a countable union. The points in 0 to 1 are uncountable if you have done any real analysis at all. And that's where the thing breaks down. This is not wrong. This is correct. But saying that the probability of the union is the sum of the probabilities breaks down when you do not have a countable list. And that's some funny things happen when you're not careful like that. All right. So as a result, how do we evaluate probabilities of funny sets? It all comes down to intervals. Eventually, if I have a strange set that I don't know what to do with, we find what is called a cover for it. And I sum up, this is countable. You find a countable, it's kind of like graphics. You have a strange design. You can approximate it well enough by boxes around it. You find a countable sequence of intervals that covers it. Then you shrink it as much as you can until it just covers it. That's what informal actually means. I'm not being exactly rigorous here, but it's like, here's a big cover for a set. I can shrink it until it's still countable. I find the smallest one. That's actually how you find probabilities of strange sets. But sometimes it's hard to work this way. So for example, what if I asked you this question? What's the probability that if I have a ruler that starts at 0 and ends at 1, I throw a dart at the ruler, what is the probability that I hit an irrational number? 0 to 1, I throw at the ruler, what is the probability that I will hit an irrational number? All right. So how do we solve things like that? So we have to think. Do we agree, first of all, that the entire ruler is the union of two disjoint sets? All the rationals on the ruler and all the irrationals on the ruler. A number is either rational or irrational, and you can't be both. So these are disjoint. So you see where I'm going with this. Now the problem is, how do I know this is even something that has a probability? I know this because if you belong to a sigma algebra, is this, first of all, a countable sequence of sets? Is this are the rationals countable? Yes. Does this qualify to fit Kolmogorov's axioms? This is something that is in our bag of sigma algebra. Now, this is a strange thing. We know that when you have uncountable unions, weird things happen. So let's not go there. Isn't this the complement of this? What's the rule? Does the collection have the complement of every set that makes it into the thing? Yes. We now know that this belongs there as well. So we sidestep the need to talk about the uncountable union here. The inherent nature of this as the complement of this ensures that both of these are in your Borel sigma algebra. And therefore, we can say things like this. You can split up the union of the probability of these two with a wonderful plus sign because of the disjointedness of the two sets. But what is the answer to this? Anyone? We are just 1 minute from closing. What is the probability of you hitting a rational number? Because this is countable, you can split this as a sum. Anyone dare to tell, not dare to tell me, anyone knows the answer to this? What is the probability of me hitting a rational number? Yes,
Zero.
it is zero. It is zero. Good. So if this is zero, does it answer our original question? Therefore, the probability of you hitting an irrational number when you throw a dart at a ruler is 1. Is this intuitive to you? All right. In other words, to use the words of the irrational numbers are infinite, the rational numbers are infinite, but one is a larger class of infinity than another. You are actually, the probability of you hitting a rational is zero. You are infinitely more likely, you are always going to hit an irrational number if you throw a dart at a ruler, and that's what's reflected by the fact that the probability of you hitting an irrational number is actually, right? You can't get a rational number, in other words, okay? So these kind of mind-bending things are what happens when your intuition fails you. Some students may think that maybe it's shared equally, or it's like a, so you see, that's where things get weird, and that's why the foundational study of probability requires this level of rigor to be able to explain. Now, please, this is not in 365, okay? This is for the purpose of this talk, but it's to open your mind to what probability theory is actually all about. It is studying things at a very, very rigorous level and understanding that everything boils down to the rules of the game. What can you do? What can you not do? What can you say? And what can you not say? And that concludes my talk. If you are interested in any of these things, please email, come see me. I'll be glad to talk to you. All right. Thank you.